Hello and welcome to this presentation on clearing the air, the effects of gasoline content regulation and air quality by Max Millen-Orfhammer and Ryan Kellogg. Today we'll be understanding this paper in detail, understanding the reasons behind this research, the novelty behind it, also wanting to look in the methodology they use, the data, and then looking at some of the results that we want to replicate. So this paper looks at the regulation in ozone and the oxides of nitrous. Ozone is an odorless gas. It's linked to asthma and increased probability of developing pneumonia and bronchitis. It's also a threat to crops and vegetation. There's two components that help form the ozone. These are the volatile organic compounds, or as we're going to refer to them throughout the presentation, VOCs. And this can be such as butane and obviously oxides of nitrogen, as previously said before. US continues to experience ozone concentrations way above the Environmental Protection Agency limits. And then the current problem is that the regulation to curb ozone concentration is causing a law of undetermined consequences. This is because the regulations which are trying to reduce the amount of ozone being released by gasoline has resulted in refineries being able to exert their monopoly power, because obviously the processes to take out these ozone causing compounds has a cost, and obviously because they're the monopoly, they can pass that over to the consumer due to the lack of competition. And what this paper will go on to, and what we will go through today, is how the regulations that the US has imposed on this, how effective are they, and is the strictness of reducing the ozone content actually efficient, because obviously the stricter the policy, the cost, the increased cost the refineries will experience in having to eliminate them. So looking at why this paper is different from everything else that is currently out in economic literature. So Henderson in 1996, a very similar paper to this one, uses panel regression and data from Environmental Protection Agency from 1978 to 1987, which is slightly different to this paper, as this looks at 1987 to 2003. And what they went out to try and understand was the effects of regulation for air quality, specifically looking at ozone concentration, very similar to this paper as well. But obviously this paper has different methodologies and using difference and regression discontinuity. Farrell et al. In 1999 researches the nitrous of oxide budget in the northeastern US to understand which regulation policy is more efficient. Again, this is sort of papers looking at understanding which regulation is more efficient, but focusing more on the ozone regulations, which we'll go into in the next slide. And then finally, another similar paper, but it sort of links to this one, is Henderson and Randy Beck in 2000 analysed the effects of air quality regulation on polluting industries. And obviously this paper looks at how the regulation and the strictness has an impact to the refineries and how that can affect the consumer if the regulation is too strict. So looking at regulation history, so the Reid vapor pressure regulation understands the intensity of VOCs that are released from gasoline, and these are measured in pounds per square inch, PSI, and this regulation limits the RVP of gasoline in the summer months. Phase 1, counties could vary from 10.5 being more lenient to 9 PSI, and in Phase 2, this the government wanted to be a bit more strict, and also it's had to reach 9 PSI in the summer months at a minimum. The reformulated gasoline regulation, RFG, were much tighter regulations than RVP. They had to contain no more than 1% benzene, which is a toxic VOC, and at least 2% had to include oxygen through oxygenate, at least 2% of the volume. And also they must reduce VOC and toxic pollution by 15% relative to other current gasolines. In phase 2, they tightened this further and reduced the VOC reduction to 25%, and then the toxic and VOC pollutants by up to 20%, increase from 15%. And then California had their own regulation where the California Air Resource Board, CARB, which was the same as RFG, limit benzene to 1% of the volume, and the RVP PSI to 7, which is a much stricter than what the the RVP was in phase 2 was setting. Also, they wanted to limit other extremely effective, reactive compounds that help create ozone, such as olefins, and they wanted to reduce that to 16%, and aromatic hydrocarbons to 25% of the volume in gasoline. And also, they wanted 80% of sulfur reduction to reduce the sulfur dioxides and oxides of nitrous. So what data did they use? So they obtained the data from the Environmental Protection Agency's air quality standards. They took a time frame between 1989 and 2003. They wanted to measure the ozone concentration through the daily maximum and 8-hour maximum. They excluded any days where no 9-hour observations between 9 a.m. to 9 p.m. That's because of the EPA standards. And they also excluded monitor years where 25% of the summer ozone season data is missing. And this is crucial because a lot of the policies are critical in the summer months to curb that ozone concentration, because obviously heat helps exacerbate ozone creation. So this resulted in a very good sample of 1,144,025 monitor days. So they also want to look at weather, because obviously there's a correlation between ozone concentration and temperature and sunlight. So they took this from the National Climatic Data Centres, took the maximum and minimum temperatures, and they wanted to calculate the prox, and to understand which station to use. And the data from which station, what they used was an algorithm which calculated the proximity of each pollution monitor and the elevation between each monitor, and the primary station was decided to be the closest station for which 50% of the pollution data is matched to the weather data. And also, another issue that this paper had was that 10.2% of that daily ozone measurements were not matched. So to fill in those gaps, they used a predicted regression measurement where the weather station was active. And to understand whether the algorithm was working, they randomly set 10% of the temperature data set it to missing, so blank, and then fitted in the predicted values. And what they found was that it exceeded 95% of what it actually was, therefore a perfect fit for this data, so they could go ahead with the methodology. So the methodology, what they wanted to understand was the extent to each regulation affects the ozone concentration. So obviously the summer RVP of 9.0 psi, the summer RVP of 9.5 psi or 10.5 psi, the summer RVP of 7.8 psi below, the federal RFG, and the CARB. And what they did was they took the summer RVP of the 9.0 as a baseline against the other regulations. And as we see later on when we go to what we want to replicate in the results, we can see some of that, of how they use that baseline to understand. And they use a difference in difference methodology and also a time series regression discontinuity design. So looking at the difference in difference methodology. So what they wanted to do is understand the regulation effects through year-on-year change in air quality. They're only interested in the seasonal peaks into August, and this is because a lot of the regulation was during the summer months, and mainly because of how critical it was to curb the ozone concentration in these months, especially as the heat can exacerbate ozone creation. They use monitors daily, maximum and 8-hour maximum, ozone concentrations from the EPA. So now looking at the first difference model, what we've got is the dependent variable, which is just a log of the monitor's daily maximum or 8-hour maximum ozone concentration. We've got the treatment effects alpha, which the treat is just each policy excluding that baseline 9.0 psi, as that's the baseline. We got a fixed effects, obviously because this is a fixed effects panel regression, and this controls for the unobservables that cause some locations to have higher ozone concentrations. Obviously, it'd be harder to compare across different counties of the effects of each treatment. If one has one higher ozone level than the other, how can you tell what's had a bigger effect? And then a second fixed effect that they put in is that they've controlled for the unobservable shocks that are common for both treated and the untreated monitors. And then we obviously got this error term, obviously the residuals. And then the second model that's taken into account. Obviously, we got the same start with the treat, but we're also taken into account the weather effects. We got the date dummy variable of the days of the week and also day of the year. We got the annual income per person, and we've also got this trend, which is basically saying it put in a unique value for each policy, and then we've got the fixed effects, obviously as the same as the first model. So now looking at the regression discontinuity design. This focuses on the change in the ozone concentration phase-in of each regulation. So it's looking at a short time space right at the start of that regulation. And why they can do this is because ozone decomposes overnight. Therefore, we should see a rapid change in that maximum ozone concentration. Which you can see for the RFG policy. You can see these steps occurring, suggesting that the RFG policy has a substantial effect on reducing the ozone concentration. To analyze using this method, they used all seasons of the year, and they also had a smaller sample than the DD, as they only allowing monitor data if they had daily recordings for more than 75% of the quarter. So now looking at this model, very similar to what we had in the first model. However, the differences that we can see, obviously we've still got the treatment effect, we've still got the four variables of which regulation. We've got the weather effect variable, and it's monitor specific, and obviously the linear time trend has now been replaced by an 8th order Chebyshev polynomial monitor specific. And what this allows, with everything being monitor specific, is that we can see spatial heterogeneity for each treatment. Obviously, because each area may have differing ozone levels, which obviously in the difference model we're controlling with the fixed effects in the second model. But in this model, because it's monitor specific, you can analyze that more easily, so it's more flexible. So the results that I wanted to replicate. So plan is to replicate the difference model, the first one, whereby the economist in this paper is trying to understand the regulation effects from year to year change in air quality following the particular regulation. Obviously, the particular regulation model is captured by the vector treat. And then obviously we have the treatment effects by A, alpha. We have the controls for the unobservable that cause some locations to have higher ozone concentrations. Obviously we're fixing that. And then we've got also we're fixing the unobserved shocks that are common for both treated and untreated monitors. So the data going to be using to replicate will be the Environmental Protection Agency's ozone monitors daily maximum and 8-hour maximum ozone concentrations, and using the time frame between 1989 to 2003. We'll be excluding all months bar June to August to only incorporate the summer months, as a lot of these policies are crucial to curb that ozone concentration in those months. We'll be excluding the baseline policy of 9.0 psi, as this will be used as a comparison against the other policies that are captured in the vector treat. So the results that we want to sort of replicate, what we expect to see, is that when we plot the RVP results from the difference versus the baseline, what we can see is that the RVP phase 2, which came in around 1992, which is a standard of 7.8 psi, has no real effect, even though it's stricter than what the baseline counties were implementing. And we can see it's not further apart than roughly about 0.01 ppm. So we can confidently say that the RVP has no effect in those counties. Now, if we go to the RFG, when it was implemented in the 1995 and onwards, we can see that there is some difference, albeit not as substantial as it would like to be. However, we could say it did have an impact on lowering those ozone concentrations. And then finally, if we look at the CARB, which is definitely one of the most successful, considering how high it was in California, and now we can see it from the 1996 massively be a decrease below those baseline counties. We can see the CARB regulation was highly effective. We also wanted to recreate the column 1 regression results, and obviously we want to look at similar results for the CARB and RFG where it's significant, and we've got similar coefficients of that treatment. Thank you for listening, and here are my references.